Okay. Now, really be careful with what you are finding out with the goodness of fit test. We're not necessarily, even though our first example was about things occurring equally alike as likely with that roll of the die, you're not testing that the categories are even. You're testing whether what you obtained, the observed values, are close enough to what is expected or what normally happens. So consider the next example and just make sure you're not thinking of goodness of fit of everything has to be even. So example 1. A manufacturer of children's vitamins claims that their vitamins are mixed so that each batch of vitamins has exactly the following percentages of color: 20% green, 40% yellow, 10% red, and 30% orange. So notice there we're not concerned about the categories being even, but we have some specific percentages that are supposed to occur. Okay, to test this claim, 100 bottles of vitamins were pulled and the color of vitamins were counted. The results are listed in the table below. So we had some helpers and we pulled off all these bottles and we sorted them out and we got 1,149 green, 1,948 yellow, 552 red, and 1,401. So what we're testing is, are those proportions similar enough and close enough to what we should be getting as the company stated? Okay, let's get into this one. So part A, determine the expected number for each color of vitamin. Well, in order to know what I should be getting, I first want to start with a total. So even though I pulled 100 bottles, I don't know how many vitamins I had altogether. So let's add up what we did get. So the 1149 for green, 1948 for yellow, 552 for red, and 1401 for orange. So that gives us a total of 5,050 vitamins. Now, according to the company, of that 5,050, 20% of those should be green. So I'm just going to take that and multiply it by 0.2. And so we'll label this down here expected. So I would expect to get 1,010. For yellow, that's supposed to be 40%. So I would expect to get 2,020. For red, it's supposed to be 10%. So again, I'm going to take my total, multiply by 0.1. So I expect to get 505. And for orange, I expect to get 30%. So multiply by 0.3. That's 1,515. So what we're testing here, notice the categories aren't all even. I don't want them to be even. But what I'm testing here is the 1,010 close enough to 1149? Is 2020 close enough to 1948, or I should say the reverse actually? Are what I got in the observed counts rather, close enough to what I expect to get? So that's going to help us with what? So this is part A, finding the expected counts. B, the null and alternative hypothesis. So for the null, you could say something like the proportion of colors of vitamins is as the company stated. And it's okay to list those out specifically. Or we could also say for null, the proportion of vitamins is 20% green, 40% yellow, and so on, and state those specific amounts. Whereas the alternative is saying that, no, that's not happening. So the proportion of colors of vitamins is not as the company stated. Okay, so we have our hypothesis done. C, we want to calculate our chi-squared statistic or test value. So remember our formula for chi-squared is the sum of all the observed minus the expected squared divided by the expected. This one I'm going to do just right here in a row. So observed for green was 149 minus 110 or 1010, that gets squared, divided by 1010 plus 1948 minus 2020. That gets squared divided by 2020. And then 552 minus 505. That gets squared divided by 505. I'm just giving you an alternate way to write this. Just some of us, our brains work a little bit different, and you may prefer to set it up this way rather than using a table. Okay, let's see what we get here. Okay, I'm getting 19.13 for this one, 2.5663 here, 4.3743, and 8.5782. And adding those all up, I get 34.65. Now that's pretty big. That's already a little suspect to me, but of course we want to continue with our calculations. Okay, part D, use alpha at 0.05 to test. So that means for chi-squared, the skew distribution here, I know that this tail area is 0.05, and I'm looking for a chi-squared that gives me that. So I go to my chi-square. Oh, got to do degrees of freedom. I tend to forget that. We had 4 colors, 4 categories, so my degrees of freedom are 4 minus 1, or 3. So I go to my table, go down to 3, and we're going all the way over. So let's erase this one. 3 and go over to 0.05, which is here, 7.815. And I think you can already tell 34 is way out here somewhere. Way, way, way off in the tail. So our conclusion would be to reject the null, and in the context of the problem, we would say something to the effect of the proportion of colors of the vitamins are not as the company stated. So perhaps there's something wrong and they need to make an adjustment with their machine, or something's going on, but what they're claiming to be the proportions in each bottle are not occurring based on the experiment we conducted. So and especially how far away that 34.65 is. We can't prove it, and we can't say just because it's much further away, but my intuition is telling me because it's so much further away, there really needs to be some adjustment so that the proportions can get closer in line with what the company states. Okay, one more. At the ER in one local hospital, nurses are convinced that the number of patients they see during a late night shift is affected by phases of the moon. The doctors just think it's an old wives' tale. The nurses decide to keep track of the number of patients they see during the late night shift over the course of a month, and their results are summarized below. So when there's a new moon, they see 85 patients, first quarter 66 patients, full moon 97, and last quarter 68. So we're going to conduct the chi-squared test of fit at the 0.1 significance level to test the nurse's claim. So you want to start off by finding the expected number of patients. So remember, in order to do that, first I have to total how many patients they saw during the month. And if I add up 85, 66, 97, and 68, that is a total of 316. Now, here they didn't give us percentages the way we had in the previous problem. But if the moon is not affecting the number of patients, we would expect to see the same number of patients regardless of the phase of the moon. So I'm going to divide that 316 by 4, and I would expect to see about 79 patients for every quarter of the, or every phase of the moon. So by saying that, what I'm saying is there shouldn't be an effect by the moon, like it doesn't matter, and that's what our null is going to be. So expected value, you want to find those first, then you want to set up your hypothesis. And our null is something to the effect of the phases of the moon do not affect the number of patients seen during the late night shift. So meaning moon doesn't mean anything, everything happens just normal. The alternative is the phases of the moon do affect the number of patients seen during the late night shift. Okay, now we need our test value or test statistic. So I need to find the difference between each observed value, the expected value, wait, that's a 79, square it and divide by the expected. Same thing for first quarter, 66 minus 79 squared divided by 79. Okay, let's see what we get for each of those. So this is my chi-squared statistic. And I'm getting 0.4557 plus 2.1392 plus 4.1013 and 1.5316. And then adding those all up, I'm getting 8.228 if I round. Okay, so there's my test value. And then for my critical value, first I need my degrees of freedom. Again, we have 4 categories, so that's 4 minus 1 or 3. And alpha was, what did they tell us? 0.1. So I go on my table, go down to degrees of freedom 3, go over to 0.01. Let's erase this previous one. Degrees of freedom 3, 0.01, 6.251. So if you need that picture. And so we're asking ourselves, where does our critical value fall in relationship, or rather, where does our test value fall in relationship to the critical value? And 8.228 is definitely in that region. So we would say for a conclusion, we reject the null hypothesis and say something to the effect that there is enough evidence to suggest the number of patients seen during the late night shift is affected by the phases of the moon. So basically, the nurses are right with their assumption. So we're not proving causality. We can't say that, but we're saying from what we expect to happen, there's definitely a deviation, and there's most likely there's something happening with those phases of the moon. So there'd be some other experiment you'd have to conduct to say, does a full moon really affect that? But we're at least saying we're not getting what we should be getting, what we're expected to get.